to the cloud. So now it's got a little cloud with a dot on it.
Yep,
That's
it's
blinking.
recording, yep, that's good. And if you click on the more dots, you can like make this guy hide.
Make which guy hide?
Hide floating meeting controls,
Oh,
unless you want
okay.
them. I mean, if you want them on your screen, you're welcome to them, but
Okay.
No, I didn't. I thought we were
Great. This is success.
do you want a drink or anything? Water?
An old fashioned maybe. No, water would be great.
I'll get some.
Are you going to introduce me? Okay, great.
I was thinking. Russia and Russia.
A little bit, not as much as I'd like. But before, it's hard because, Russia these days is not a real country anymore. It's a monster, and it's really hard to be so long. Oh, okay. It's hard to be so tightly affiliated with all of that. What's going on. It's really difficult. But I did go, last time I went to Russia was in 2018. Right before the pandemic. There's feedback. And I got to speak at a conference on AI in Moscow, and Putin showed up to give a speech on AI, which was actually a really good speech, much better than any speech that I never heard an American politician do about AI. Although it was very nationalistic, he was talking about how it's a spooky moment for Russia. Whoever controls AI is going to control the future of the world, and it should be Russia. And then they asked me on live television to prepare to answer this question: who's better at AI, the US or China? Does Russia have a hope of catching up? And so I worked a lot to prepare a very diplomatic response in English. And then I hung out all day with all these oligarchs. Putin was there, and they're like, "Oh, you speak Russian, great. You should just answer in Russian." So then I was sitting there trying to put my vocabulary together because I know much more about AI in Russian. So I was learning all these words and getting ready to say it. And then the guy asked me instead, he asked, "Can you tell us about the equipment that's necessary to build artificial intelligence?" It's okay, a much easier question for somebody working at NVIDIA to talk about. It's certainly much better geopolitically for me to not talk about all these things. But of course that meant I wasn't prepared at all. I had to make it all up. So.
Oh, that's fine. Yeah, I'll just test it out real quick. Sorry, listen to that side. Oh no, just the speaker. The speaker. Yeah. Okay, can mute. You're muted right now.
I don't really, when I hear people speaking Russian, I usually don't strike up a conversation. We're just sort of, oh, great. Yeah. Oh, great. Were you in Santiago or? Yeah, my mission was the biggest mission in the world at the time.
No, yeah. Is that
It was called, the one I was in was called the Exchange, which had a lot of Kazakhstan and a lot of Siberia. Then there's also the Novosibirsk expedition and the Vladivostok expedition at the time. I don't know. They're always changing boundaries around, so who knows what they have now.
Thanks, Terry.
Thank you.
So Zoom, we think we're good. Zoom, we're good. Is it okay on my phone? I can see it. Okay. All right. Okay, great.
Yeah.
Super. Okay, no. have the restriction on food and food in here now?
That's we had our maps on.
Oh, that's right. Okay. No math. No math.
I'll be in
Which I-
Mineola, but I'll start to do. You for now got the live. The Zoom is live, so mute it. So that it-
Uh,
Fascinating conversation.
let's see.
Were they able to hear?
There's an echo, but I think because of this.
Welcome, everyone. It's a little loud. Delighted to welcome everyone to the first of our two keynotes at WACV 2023. For those of you just coming in, there's still a bunch of seats over here on the speakers right, your left. It's a pleasure to introduce our first speaker, Brian Catanzaro, is Vice President of Applied Deep Learning Research at NVIDIA, a position he's held for almost 6.5 years. Brian holds degrees from Brigham Young University, a bachelor's and master's degree, respectively in computer engineering in Russia and electrical engineering. Brian received his PhD from UC Berkeley, working with Kurt Kutzer. And he's been at NVIDIA for much of the time since then, along with a couple years at Baidu. Brian leads a team at NVIDIA doing AI research on chip design, audio and speech, language modeling, graphics and vision, all with the goal of finding practical ways to use AI for NVIDIA's products and workflow. Products like DLSS, Megatron, cuDNN, Pascaline, WaveGlow, and Deep Speech are some of the projects that he's helped create. The title of his talk today will be Neural Rendering Computer Vision for Post-Moore's Law Graphics. I think a lot of those applications I mentioned we'll get to hear him talk about. And please join me in giving Brian a warm welcome.
Thank you. I'm really glad to be here. So you may wonder, why am I here talking about graphics at WACV? Isn't this a vision conference? Well, so I think it's becoming clear to all of us working in this field that analysis and synthesis when it comes to visual representations are tightly interconnected. And it turns out that the better vision that we have, the better graphics we can make, the better graphics we have, the better vision we can do. And so there's kind of a loop. And things are starting to get a little bit blurred as to whether or not something is vision or graphics. For example, is this vision or is it graphics? How many of you have played around with these selfie apps? They're pretty fun, right? In fact, I don't know if you can tell, it even has my glasses right. You know, if you think about the amount of analysis that had to go into something like this, there's an extraordinary amount of computer vision, but it's also a synthesis process. You know, we're using these representations to synthesize new views of things, entirely maybe fictitious scenes, for example, and that's you know usually called graphics. So it's both. Okay, so that's why I'm here talking about graphics at a vision conference. Also because, you know, I work in NVIDIA, and NVIDIA cares deeply about both vision and graphics and AI, so it kind of makes sense. Now, why do I want to talk about Moore's Law? So, you know, Moore's Law is one of these myths of the computing industry, and it means something different to everyone. But if you actually go back and look at the original paper from 1965, in big letters at the top of the paper, it has this quote, with unit cost falling, that's talking about the cost per transistor, as the number of components per circuit rises, by 1975, so that's 10 years after he wrote this paper, economics may dictate squeezing as many as 65,000 components on a single chip. So, you know, we've had 50 years of Moore's Law, and what that has meant for the entire computing industry, but especially for graphics, has meant you know, we've been able to dump compute into the problem and solve things in, you know, very brute force ways, because there was always the next chip coming along, and it was going to have twice the number of transistors in it, and so we could do more cool things in it. Now, at NVIDIA, we like to say that Moore's Law is dead. Our CEO, Jensen Huang, has been saying that recently, and you know, why would we say that? Well, we're still actually building more and more awesome chips with more and more components, but the amount of power per chip has been creeping upwards, and the cost per chip has also been creeping upwards. So the that first predicate with unit cost falling, you know, that's just not true anymore. It's going down, but not nearly at the rate it was before, and sometimes it's actually going up for a while. So like the newest and most awesome transistors will be more expensive. And then, you know, the other thing I wanted to highlight here is that this statement, at least the way that Gordon Moore wrote it, is an economic statement, right? So if the cost has stopped falling, then the economic argument doesn't make sense anymore. And that's what we mean by is Moore's Law dead? How many of you have built computer vision models on a GPU before? Raise your hand. Okay, I see almost everybody raise their hand. That makes me happy. You know, back when I wrote cuDNN, it was kind of a weird thing. Nobody cared about computer vision on the GPU in that way. And you know, we've come a long ways since then. The reason that NVIDIA was able to build processors for AI for computer vision experts like you is actually because of graphics. So we had this amazing engine going where we just were dumping resources into making the most awesome GPUs, and it turns out they were pretty good for AI as well. We could make them be good by adding the right features to them. So we've been doing that for a while, but now Moore's Law is ended. So what are we going to do? You know, at NVIDIA, we believe in accelerated computing, which is this idea that in order to solve the most important problems in computing, we need to visit all of them together. So algorithms, applications, libraries, frameworks, compilers, systems, the silicon, we're going to optimize all those things together. And you know, that's why I'm here talking to you guys today, because you guys are experts in applications. This is an applications conference. And it turns out that with the end of Moore's Law, now we're starting to push more into redefining applications in order to be smarter, in order to solve problems with less brute force and with more intelligence. At the same time that we have this need, because, you know, transistors are getting more expensive, we also have incredible new tools, such as the kinds that all of you are inventing. You know, all of you that are giving papers here or talking about your research to your friends here, you're all part of this community inventing new tools that, you know, analyze images, synthesize images, and all these things are related. Now, graphics is really an important workload, and although maybe it's often thought of as separate from vision, I just wanted to point out, you know, the reason that GPUs have been pushing so hard for so long is because people really want better graphics. They want better lighting, materials, geometry. They want better animations. They want better physical simulations. And they want to compose all of those things in virtual worlds that enable them to experience new things and solve new problems. And it's actually almost an infinitely complicated problem. You might remember the talk about this is water. I just took a picture of a glass of water from the internet. And if you think about the complexity of the lighting, the materials, the physics simulation as the ice is sitting there melting, there's even a droplet of water on the glass that's refracting light. The complexity inherent in a glass of water is extraordinary. And we're pretty far from being able to solve that with computer graphics now. So we need better graphics. But that means if Moore's law is ending, we have to revisit everything, and we especially need to look at applications. Is there somebody that's working on the feedback? Okay, I'm gonna gingerly keep talking. Thank you. It's just really unpleasant for everybody to have the ringing going on. Okay, so the sort of idea from that I wanted to talk about today is that I think that neural rendering is the path forward, and basically computer vision is going to build us the bridge to a future that has better graphics for everyone. And why is that? Why do I believe that? Well, rendering is highly correlated both in space and in time. If you think about a video signal, it may be like 8 megapixels per frame, and you might have 60 or 120 frames per second. So if you think about that, that's an extraordinary amount of information that we're processing visually. And it has to be that there's tons of correlation in that. Otherwise, it would just be like Gaussian noise, right? No one wants to look at a screen full of noise, right? So there's structures in there. We could use that. Why do we need to compute the color of every pixel, so frequently when there's a structure there we could work with. We also know that rendering is a learnable process. So if you play around with models like some of these generative models like Stable Diffusion or DALL-E 2, you'll see that they're already starting to do rendering. So things like refraction, shadows, lighting, global illumination, these things that in the past we have simulated in graphics with bottom-up calculations about how rays are intersecting with materials, we're now actually learning those equations implicitly through deep learning. So we have new tools. We also have a problem with a lot of correlations in it, but it's a difficult problem. The requirements are very stringent. People want computer-generated graphics to be pristinely beautiful, and they want them to be perfectly controllable. And they want to have artistic expression. They want, to make the virtual world they're creating fun and safe. And, all of these things are challenges for completely implicit methods. But, it's a really exciting field to work in. And it comes at a time when we also need to solve these problems for other reasons, like CPUs are remaining slower than GPUs, which means that graphics that depend on the CPU to build up the scene every frame are starting to fall behind because the CPUs just can't keep up. So all these things come together and make me believe that the future of graphics after Moore's law is neural graphics based on computer vision. So let's talk about that a little bit more directly. I'm going to be talking about 3 different applications that we've been working on at NVIDIA. They kind of are at different levels of abstraction. We have at the bottom pixels. I'm going to talk about DLSS, which stands for Deep Learning Super Sampling, which is a product that we build using computer vision techniques that renders video games using neural networks. And I'll talk about that. I'll talk about Magic 3D, which is a new text to 3D project that we've started, and then also our Edify model, which is a text to image and text to video model. We're going to start from bottom up. Okay, so DLSS, Deep Learning Super Sampling. The goal of this technology is to make virtual world rendering more efficient by using AI. We have a multi-dimensional space. Any computer graphics technique is going to be trading off smoothness, which is the cost that it takes to render a frame. We call that FPS. Also, related but different is the consistency of the frame time. So people want the frames to show up at a very regular cadence. Then we have responsiveness, which has to do with the system latency. When you press a button, how long does it take for something to happen in the virtual world? We want that to be low because it makes it feel like you're actually playing the game. And then we want image quality to be high. So image quality, there's tons of different dimensions. I'll talk about some of them, but there's still image quality, which has to do with things like aliasing or detail, as well as motion quality. So when something's moving, we want it to be temporally consistent. We don't want flickering. We don't want ghosting. And so these are, I would say, the three main axes that we're going to be optimizing. But graphics is a trade-off. It's always a trade-off. And what we're trying to do is push out a Pareto frontier. We want to push the speed in terms of push the boundary in terms of what we can do at any given image quality level, increase the speed, or the other way around. Just to give an example of this, on the right is 3 different rendering techniques that are all running at the same frame rate on the same GPU. These are actually products. So this is not just like things in the lab, but this is actually released products. And if you look at them, you can see that one of them has a lot less ghosting than the other two, and the one on the right has tons of ghosting, right? So they all have the same speed, but if you're going to render, people would ordinarily prefer the one on the left. So that's what I mean by we've got this like highly dimensional trade-off space. It's usually the case that you can make speed better at the cost of introducing more ghosting or more aliasing or more moire or flicker. And we want to try to use computer vision to push that frontier out so that we can continue delivering more efficient rendering, even without just dumping transistors. We want our rendering to be smarter. So a few months ago, we released our 3rd version of DLSS, and it uses neural rendering to generate 7 out of every 8 pixels when you're playing a video game. At least a video game that has this library integrated into it. And the way it works is that it does spatial upsampling at a 4:1 ratio. So you go from 1 pixel to 4 pixels in one frame, and then it does a temporal upsampling where it invents entirely new frames and interleaves those. So we're doing both interpolation as well as upscaling using this method. So I'm going to talk a little bit about how that works. One of the reasons why we felt the need to push on AI accelerated rendering is that rendering is always too slow. No matter how much awesome GPU power we have to compute the scene, there's never enough. We put in special purpose ray tracing hardware to do ray tracing calculations, and yet when you're playing like the most awesome games, the frames per second is still too low. In this example, we're looking at something from Cyberpunk. We're rendering the game using ray tracing. We're getting 23 frames per second at 161 milliseconds of system latency. And those numbers don't make people happy. People generally don't like playing games at those numbers. So we're going to try and improve that. Our second version of DLSS, which I'm going to be talking about today, will introduce this super resolution where we take motion vectors from the game as well as past frames, and then we stick it through an autoencoder in order to generate new frames, basically using information from past frames and sort of trying to do an integration over time. And that allowed us to go from, in this game, this is a real game, Cyberpunk 2077, go from 23 frames per second to 62 frames per second. And the latency went down from 161 milliseconds to 58 milliseconds. So that was pretty exciting. And that is running at 4x upsampling. So 1 out of every 4 pixels is rendered traditionally, and then 3 pixels are being generated by DLSS. So how does this work? We worked for many years building this network. Involves a lot of custom data sets that we've built and a very carefully crafted algorithm. As most things, the deep learning network is in the core, but then there's a lot of pre and post processing that we use in order to sort of prepare inputs to this neural network and then interpret the outputs in order to generate the results. This product, I think it's been pretty well accepted by gamers. People like playing with DLSS. Maybe some of you have played with it before. It can go 4x upscaling ratios. We spent a lot of time working on making a generalized model so that we didn't have to train a new neural network for every game that came out. And that was actually kind of difficult because it turns out that every game has a slightly different look. And the models were overfitting a little bit, which was leading to visual artifacts that we didn't like. And like things were blurry and blocky. And so, we had to do a lot of work to figure out how to get the model to generalize. And then, of course, we did a lot of work to make it run fast. It runs, in order to produce a 4K image, it takes half a millisecond on our latest GPU. So it runs really fast, and that's part of the value of this technology. Again, this is a multidimensional problem. So every microsecond that we spend running the neural network is going to take away from the reason why we're doing this, which is to try to accelerate render. Just a little bit more on how this works. DLSS1 was primarily a single image super res algorithm, and I think it was a really brave product when we released it in 2018, but it didn't really work because the resulting images just weren't detailed enough. They didn't look high resolution. It looked like the neural network was just making up stuff, and it wasn't, and the results was kind of blurry. So that has to do with the problem that we're trying to solve. We have an undersampled signal we're trying to reconstruct. If you just ask deep learning to fill in the details, it can do that, but it's going to do that in maybe a kind of low quality way. Just didn't work very well. And so we had to re-engineer that with DLSS2, and we were looking around, and there were some great computer vision papers on multi-frame super resolution, primarily for cameras. So when you take a camera, probably some of you know this, in fact, maybe some of you invented algorithms for doing this, that when you take a photo on your camera, it takes a video and then uses some integration process to try to use multiple samples from multiple frames to come up with the final image. Of course, the question is, how do we do that integration? Because some of those samples are going to be wrong because things move over time, right? And so you need to have some sort of a model that's going to guess, like, for every sample that you get, can I use this sample to integrate for my signal, or should I reject it? And so there's these works on multi-frame super resolution, and the DLSS2 super resolution is related. What we're trying to do is, again, solve this integration problem across multiple frames. And of course, if you do it wrong, then you're going to get artifacts. You're going to get ghosting, flickering. If you use, that's what ghosting is, right? If you use a sample from a frame, but the thing has moved, and so you're going to show the thing where it was before, but it's not there anymore. That looks like kind of an after image. So so that's kind of the problem that we're trying to solve with DLSS super resolution. We train a neural network on a big data set that we've built, and I think this has been a pretty successful product, and a really interesting way of using computer vision for one of NVIDIA's core businesses. Like the way that people buy GPUs to play video games is sort of by the size. It's kind of like, how many pounds of GPU are you buying? And so if you're able to make like half a pound of GPU look like 2 pounds of GPU because computer vision made your rendering your algorithm smarter, then that's pretty exciting for our customers. So this is what it looks like. I just picked some benchmarks from one particular game where we were seeing a 2.7x speed up. So remember, this is 4x upsampling, so we're doing 4 times less work on the GPU. So the maximum speed up would be 4. But then, of course, there's the cost of running the neural network and also scheduling it and everything else. So in the end, we get 2.7x. That took a lot of systems work as well in order to make that happen, which, again, maybe some of you have done that. Maybe some of you have worked on real-time computer vision algorithms, but it's the very same thing. Okay, how does it look? It's maybe hard to see on the slide. You can Google reviews, and there's lots of content on YouTube about how this works, but maybe if you look on the right where it's zoomed in and you look at the text where it says caution, wear protective equipment, the left is a crop from an 8 megapixel native image, and the right is a crop from a 2 megapixel image that's using DLSS. So it's 4x upsampled. And, I think it looks pretty sharp. And that was the goal. So So we're pretty excited about that, but it's not enough. We want to do more. And so that's where interpolation comes in. Now, interpolation, another important computer vision problem. In fact, I'm sure there's some papers on interpolation at WACV. I think I saw something in the award ceremony about one today. So we're thinking about that too. What could we do for computer graphics with interpolation? And so what we built with DLSS3, we actually have a hardware unit that generates an optical flow field by using kind of a hardware search method. So it's not particularly smart. It's just kind of related to video encoders. That's going to generate an optical flow field, and then we're going to stick that in another neural network in order to generate entirely new frames. And you can imagine that this is also a really challenging problem, but here's how it works. So we're able to go from 20 milliseconds to 20 frames per second to 100 frames per second. And latency goes from 169 milliseconds to 60 milliseconds in this particular game. Here's another game, Flight Simulator, where we're able to go from around 50, 60 frames per second up to like 130 frames per second. So we're doubling the speed. Now, the reason why it only doubles here is that this game is actually CPU bound. So if you think about the process that's going on with Flight Simulator, it has an entire world full of, Paris or San Francisco or whatever it was that we were just flying over. And, every one of those objects, this is Paris, every one of these objects is being simulated by the CPU. And there's, I think that's San Francisco. That's really CPU intensive. So it doesn't matter how fast you make the GPU, how efficient your rendering process is, if you're still dependent on the CPU to do that modeling. But again, we have correlations in this video sequence, so why don't we take advantage of that? So we can actually use that to get a speed up even when we have a CPU bound game. So just a little bit more about the problems here and how we worked on them. The potential of frame generation or interpolation for video game rendering, I think, is pretty clear, because you can create a lot more smooth animations and overcome CPU bottlenecks and reduce the amount of work that the GPU has to do. So that then you can invest all of that GPU power in more beautiful graphics, better simulations, ray tracing, and things like that. Now, real-time interpolation in a graphics rendering system is actually really hard to do because of latency, for one. And so we had to work really a lot in order to overcome sort of the latency challenge. And I think if you talk to people about doing real-time interpolation, most times the first response would be, but what about the latency? What about the latency? Isn't that going to make it feel bad? Well, it could if it was done wrong. And I'll talk a little bit about how we make it better. But I also want to say that one of the things that's interesting about this is that when you use the system to generate an intermediate frame, it's true, you are delaying the true frame that was rendered. But the intermediate frame that you're generating actually contains information from that true frame, right? So if you're measuring how long does it take from when you click a button for a pixel to go from black to white, the interpolated frame is going to be gray in that pixel, which is not white, but it's also not black either. So the perceptual latency is a little bit more of a complicated story. Okay, so a little bit more about the optical flow accelerator. You guys are computer vision experts, so I don't have to explain too much about what optical flow is. We have motion vectors from the game. The motion vectors from the game are giving us sort of a geometric view of how objects are moving, but they don't see how things look, right? So if you look at the road, the geometric motion vectors from the road are going to be moving past the camera, right, with the ego motion of the camera. Well, if we just use that to warp the frame, then what we get is this shadow getting dragged along with the road, right? Because the shadow is lying on the road. There's no geometric motion vectors that tell us that shadow exists because it doesn't have any geometry. It's a lighting effect. And so that's why we need optical flow. But as you guys know, optical flow algorithms, whether they're built-in hardware or whether they're running in deep learning, they're an approximation because optical flow is an ill-posed problem. And so there's going to be some errors in that. When the motion vectors are right, the motion vectors are sub-pixel accurate, right? Because they're telling us exactly where the geometry is. And so we have, again, kind of another problem. And wouldn't it be great if we had deep learning to try to learn a model that can use all of these things together, right? So we train the model both with vectors from the game as well as optical flow that we're computing, and then we are able to synthesize, an accurate reconstruction. Now, I've been pointing out the shadows here. Shadows are one problem, but there's tons of other problems that are very difficult for interpolation. Reflections, for example, geometric motion vectors are not just wrong, they're like all the way wrong, for a reflection, because the thing is moving in a different direction from the object. What about the user interface? So when you play a game, there's usually like a gazillion little markers on it that are telling you important information about where you need to go next, or who might be hiding around the corner. That information is really important to playing the game, and it also needs to be interpolated. So we have an interesting problem of trying to identify which pixels are part of the UI, which pixels are sort of going to be moving independently of the geometry behind it. What we don't want to have happen is that the game is dragging the UI along with it, kind of in the same way that shadow is being dragged around. It'll start flickering. So you can tell this is an interesting problem, and we haven't completely solved it. There's still artifacts that we're working on, and if you go read the DLSS 3 reviews, they'll point them out. That's one thing the internet's really good at, is helping us improve our models by pointing out where they fail. But we are making a lot of progress, and a lot of the progress has to do not with deep learning per se, but with sort of the framing that goes around the deep learning. What's the inputs and the outputs to the model? How can we sanitize them? How can we make it safe so when the model mispredicts that we don't do a thing that's like really jarring? So there's a lot of innovation that I think this is pretty common for computer vision applications, right? Like you have some machine learning model, but that's not the thing you ship, right? There's a lot of things around it that turned into a real application, and it's no different here. Okay, I wanted to talk about latency just because I know it might be on some of your minds. Well, it turns out that the way that systems have worked up until a couple years ago, and only at NVIDIA, no other GPU manufacturer has figured this out yet, is that the CPU is building up command lists to send to the GPU to render for every frame, saying, okay, draw everything, and there's a lot of things to draw, a lot of draw calls. So it takes a lot of work for the CPU to do that. What you don't want to have happen in the system is for the GPU to run out of work, because then your throughput's going to go down, right? So what you want to have is a queue that's stuffed all the time with work for the GPU to do. And then the GPU can run at full tilt and make the highest possible frames per second. But adding in a queue that's filled with work all the time, that's introducing latency. And so in a traditional game rendering environment, including every game that you guys have played, unless you've been playing recently on an NVIDIA GPU, there's this big render queue that can have significant amounts of latency, 20, 30, sometimes 40 milliseconds of latency just sitting in there. And it's the reason that exists is to try to keep the GPU busy. But what we've been able to do is remove that, because if you think about it, like you imagine like the Toyota car manufacturing just-in-time philosophy, like they're trying to like bring the components together that day, right, when you build the car, so that you like reduce your inventories, right? If you think about that, we have a similar problem here. Like if we could figure out some heuristics about how to synchronize the CPU and the GPU here, then we could actually get rid of that queue and reduce the latency without lowering the throughput of the overall system. And so that's one of the components of DLSS 3, and is one of the reasons why we're able to get such good results. These are results that are measured by Digital Foundry. They're a website that looks at graphics technologies, so this isn't coming from me, but you'll see that they're comparing native 4K, DLSS 2, so that's super resolution only, DLSS 3, which is adding in frame generation. And you see that we're getting the frames per second is going up quite a bit. On this game, it's a very GPU heavy game, so we're getting 5.3x speed up. And remember, this is using computer vision to generate 7 out of every 8 pixels, right? So the maximum would be 7. We're getting a speed up of 5.3 here, including all the overheads needing to run all of these networks and schedule them interleaved with the actual game on the GPU. Now, the other thing to look at is these reflex columns. So if you look at native 4K rendering, so without any DLSS. We're at 129 milliseconds with reflex off and 95 milliseconds with reflex on. So turning on reflex, we were able to subtract about 35 milliseconds of latency from the game. Now, if you think about a frame time, like at 60 frames per second, that's 16 milliseconds per frame, right? So that's basically 2 frames worth of latency at 60 frames per second. It's a lot of latency that was sitting in that queue. So we're able to pull that out. And so at the end of the day, with frame generation, with our interpolation turned on, we require that reflex is also present. And then our overall latency is only 56 milliseconds. So if you put it all together by using computer vision in this particular way, well, along with a lot of other stuff, then we're able to raise the frame rate of a game by 5x, and we're able to cut latency in half compared with standard rendering. So that's pretty exciting. And again, this has to do with being smarter about how we go about the rendering process. This is just a bunch of charts showing for a bunch of different games that we get a lot of speed up. And the speed up is lower on older games because they're not as compute heavy. So newer games, especially games with tons of heavy ray tracing in them, are much more GPU bound, and so we get a lot more speed up. So that was what I wanted to say about DLSS. I think it's an exciting application of computer vision. We're at NVIDIA, we're transforming the way that computer graphics is done sort of at the pixel level by using things that and love, optical flow, segmentation, autoencoders, a bunch of standard techniques that you guys know about. Now I want to talk for the remaining 10 minutes. I want to talk about some other neural graphics work that we've been doing. And I'm gonna talk about a new project that we recently posted about called Magic 3D, which is a text to 3D model project. And one of the reasons that we're working on this is that we have this dream of virtual worlds that are ubiquitous, not just for games, but also to solve real problems, like, for example, architecture and design and collaboration of various kinds. Meta recently renamed itself and has been investing a lot in the metaverse. And we also believe in the future of these sorts of environments, but one of the bottlenecks to creating them is actually getting assets into these environments. So if we could have ways of building assets, that would be really helpful. So this project takes text and produces a 3D model. And here's a few results. This is all public. I'm not going to go into a lot of the details on it, but if you're interested, you can look it up on this website. And I think it's doing a really great job of sort of high resolution mesh creation out of just a text input. And when you think about that, it's really exciting to think about the power of these embedding spaces. If you would have asked me like 20 years ago if it was possible to build an embedding space for text and 3D meshes that was this good, then I probably would have said no. But the computer vision community has been working really hard, and deep learning community, and it's kind of incredible the things that we're able to try now. It makes me wonder what kinds of embeddings we haven't learned yet that are going to revolutionize other applications. I think that today's graphics environment is still built primarily around traditional graphics primitives such as triangles, materials, lighting, and so it's an interesting question. How can we redefine all of those using some kind of embedding so that we could actually learn them from real images, from real videos, and then hopefully make our graphics better. And then I wanted to end with a discussion of our Edify work. I know it looks kind of like Edify or something like that, but that's the name that was chosen for this project, Edify. It's supposed to make us feel smarter somehow. There's been a lot of progress in text to image diffusion models recently. And, we're really excited about the prospects of generating entire scenes using these embeddings, where all of the rendering is happening inside of some implicit process. And here's some outputs and some inputs from our Edify model. One of the things that I think has been challenging with very implicit generative models is controllability. How are we going to use this as a graphics technology when we really don't have a lot of control about where things show up and how they look? And so we've been working on that. Here's a video. It's sped up just for the sake of our time here. But what's happening in this video is that you're drawing a cartoon with different blobs, which you then get to assign text labels to. So you may have seen, we've been doing work on this as a community for a long time, and I've been involved in some projects like Pix2Pix HD. You may have seen some projects that could do similar things with semantic labels, and the way they worked is that the sort of embedding space was a set of 20 different semantic tags, because the Cityscapes benchmark had 20 different classes of object in it. And so we trained a semantic segmentation model on Cityscapes, and then we used it to generate images, and it was restricted to generating things that were of the 20 classes that were in the Cityscapes data set, right? So you've probably seen a lot of these things that were done with semantic labels that had a fixed set. But the thing that's I think so exciting about this is that it's not fixed, right? It's just language. So you can write anything you want and attach it to one of those cartoon colors and control the output. Here's another one. Highly detailed digital artwork of a rabbit mage standing on clouds casting a fireball. So we said, where's the rabbit? Where's the fireball? Where's the clouds? One of the things about the Edify model that I particularly like is that I think it's better at text than some of the other models like Stable Diffusion and DALL-E 2. The reason for that is we have a richer embedding space. I'll talk about that in a second. But it's spelled NVIDIA correctly, which always makes sense. By the way, maybe not all of you know this, but NVIDIA means envy in Latin. And it also means looking within, right? So video meaning looking, right? So anyway, NVIDIA is all about the evil eye, which is why our color is green for envy. Okay, so there you go. NVIDIA rocks. So of course the t-shirt needs to be green. 2 Chinese teapots on a table. One pot has a painting of a dragon. The other pot has a painting of a panda. So we're pretty proud of the fact that we actually did get 2 teapots, and that there is actually a panda, and the dragon I'm a little bit less convinced about, but it's dragonish. This is exciting. The Stable Diffusion, I feel like the picture that it got up there is a painting of a panda on the wall, but it didn't put it on the teapot. So clearly this embedding space is learning about how objects interrelate spatially, and that's exciting. Now, one of the things that we did in this project was to use an ensemble of expert denoisers. So if you think about the task of text condition generative denoising process, the task is different at different parts of the process. At the beginning, you're starting from an image that's basically noise or very close to noise, has very little signal in it. And at the end, you're basically doing like super resolution or cleaning up, some very slight noise removal. If you think about it, it kind of makes sense that you might want to differentiate those models, because the task of like assigning where objects go at the beginning of the process where there's hardly any information is kind of a different task than the task of cleaning up the image once everything's placed and just like fixing all the final details of like where every single hair goes. And so the idea is that if we break up the model, instead of having one model that we repeat over all the different steps of diffusion, we're going to have many models, and we're just going to switch between them during the diffusion process. And that helped us a lot. And then, the other thing that we have here is stronger encoder, stronger embedding. I think we are using both the clip embedding as well as a T5 embedding, and then also a clip image encoder, so that we can use a style reference as well, if we want to. It's optional, but you can if you want. So you can read about that also on this website if you're interested to learn more details and read about the things in more detail. And then finally, we've recently extended this to create videos. So here's a few: a jar full of fire, photorealistic video of 2 squirrels boxing match in an elegant bar, a very happy panda dressed as a chef making pizza in a New York food truck. Now these videos are not good enough to be a game rendering engine yet. If I showed these to our DLSS customers and asked them, to play a video game with these squirrels, they would be like, I'm sorry, that's a cartoon, that's not real yet. But the fact that, we're able to make them move in sort of coherent ways, I think is kind of exciting. As early research, I think this is really, really pointing the direction to graphics of the future. Okay, so I wanted to end with a call for help. There's a lot of challenges for generative models, and maybe some of you are already working on them, but I wanted to highlight them as well. If we envision a future, post Moore's law graphics future where everything is being done by computer vision generative models for graphics, we need those graphics to be controllable, so that all the objects are exactly as we specify. They need to have the right textures, they need to have the right shapes, they need to be in the same positions. And we need to have consistency. So there needs to be some sort of way of navigating a virtual world and closing a loop, coming back to where we started from, where we see the same object, maybe from a different perspective, but it's still clearly consistent. With completely implicit representations, that's pretty hard. And then, interactivity. So, with DLSS, I was telling you about how the model takes, half of a millisecond to run at 4K. Well, these diffusion models, they take forever, right? And maybe some of you have played with them. They can take seconds to run. We need that to be milliseconds at most. How are we going to get there? I think part of it's going to be customizing our hardware. So, at NVIDIA, we're always trying to figure out what the most important use of the GPU is. And so I'm going to go make the case that diffusion models are the most important thing to run on the GPU, and see what I can get from the GPU architects. Maybe they'll put in some special things for me. That would be cool. I think also the algorithms need to improve as well. When I was talking about accelerated computing at the beginning, I said no technology left behind. Figuring out how to run diffusion models faster with fewer steps and still get awesome results, I think that's really important. So generative models, these challenges are really important, and I can't wait to see how the community pushes that forward. And then also, we have a continued need for advances in more fundamental computer vision tasks. So, I mentioned segmentation a bunch of times, which we use a lot of. I mentioned optical flow. Optical flow is clearly at the heart of interpolation problems, and we'd like to make it better. Embeddings, so this future of neural graphics, I think, revolves around embeddings, but nobody really knows what the right embedding is. So we embed text, we might embed pictures. We could even embed videos so that we could, resynthesize a video of me giving a talk into Jensen Huang giving a talk, or, something else fun. But, we don't really know what the right interface to such an embedding should be. And I think there's a lot of interesting research just to try to figure out, like, what is the space that we're going to embed all this stuff into that gives us controllability and consistency, and hopefully also helps with interactivity, because all these things are related. And then finally, the other cry for help that I wanted to put out is loss functions. Oh my goodness, do you know how much time we spend fighting our loss functions? Yes, you do, because you're also fighting them. We have terrible loss functions. We need better loss functions. Like, we can't really even reliably measure ghosting in a loss function, which just makes me angry. Of course, like, we've been working on it. We have some things that are correlated with ghosting that we can measure. But like, at the beginning, I said that computer vision and computer graphics are kind of in a cycle, right? The better vision we have, the better graphics we can make. There's still a ton of work, I think, on loss functions in order for us to measure things like aliasing, Moiré patterns, ghosting, flickering, even image detail. What does it mean to measure the image detail? Well, that's a hard thing to say, but I'll tell you, when I ship a DLSS version that's blurry, YouTube measures it instantly. The reviews come back pretty harsh. In fact, with DLSS 1, which didn't work as well as we wanted it to, somebody made a video where they put Vaseline over the whole camera, you know, and they like did some haunted house kind of, you know, worst products of some year because, you know, DLSS was blurry. So, you know, we fixed that with DLSS 2, but, you know, it would be great to make it better, but it's hard to do that when we don't even have a metric to measure, like, is this image blurry or not? That's actually a really hard problem to measure. So if any of you are making progress on that, that would be really great. And then just to wrap up, you know, I have this belief that neural rendering is the future of graphics. We just can't afford to do business as usual because we can't just dump more transistors into graphics. Graphics is such an important workload. It's enormously valuable. There's so many applications that people rely on and people enjoy built out of graphics. But you know, we have to be smarter about how we generate graphics, and being smarter about that means using more computer vision in the graphics process. And so that's my belief. And I also wanted to, you know, highlight that we are making progress. You know, the fact that DLSS is rendering 7 out of every 8 pixels using computer vision, and people generally like playing with it, I think is exciting. Of course, we want to make the models better and have even fewer artifacts. And then we want to push models even farther so that more and more of the process is being done completely generatively. And all of this relies on computer vision, which I think is the way forward for graphics in a post-more world. That's it. Thank you.
Thank you, Brian. We have, I think, 3 microphones spread across the room in here. Also, for those maybe in the overflow and or watching remotely, there's the app, the virtual platform. While anybody's coming up, if you have a question, go ahead and stand up if you're in here. One question that came in through on the virtual platform from Sam Greenberg. You mentioned generalizing to a variety of games. Are you worried some new style will stray outside that generalization? For example, if I run DLSS on Pac-Man, does it generate a terrifying, uncanny Pac-Man face instead of the always profile original style?
Yeah, I mean, so that's a great question. And, you know, with DLSS 2 super resolution, we're not actually hallucinating very much detail at all. You know, the problem that we're posing is more of an integration. So we're trying to use samples from the past, but we have to do that intelligently, because if you just accumulate, then you're going to ghost every time something moves or a light or shadow changes. So for DLSS 2 super resolution, we're not actually going to hallucinate what Pac-Man looks like. Hopefully what we're going to do is fill in the details really well. I forgot to mention when I was explaining this that the camera is jittering during that process. So every frame has usually a halting sequence, like maybe 32 taps, where you're moving the camera around, which sort of lets you see around corners just a little bit, gives you some more samples, and that helps with adding more detail to the final result. And that's actually the reason why sometimes DLSS 2 super resolution has more detail than natively rendered things, because, you know, if you manage to integrate more information, then you're actually going to be able to resolve things like fine lines and other image detail better than a traditional renderer. So sometimes we get that. Other times our model messes up, and then we get ghosting and moire and, you know, other undesirable artifacts. So the problem with Pac-Man, if it never seen it before, if it failed and generalization was broken, is that, you know, things would be ghosty or flickery. It would probably be the thing you would notice.
Hi. So thank you for the great talk. I was wondering about fine-tuning to something like fine-grain recognition or fine-grain problems with these kind of generative models. And so one of the questions is, if it's never seen a new style before, how is there a way to be able to make it creative or to extend this kind of interface to be doing something we've never seen?
I think so. You're talking primarily about like image generation models, or which kind of models? Yeah.
Like a 3D, it could be the 3D stuff or the video stuff as well.
Right.
The question is, for these kinds of interfaces, how do we even program in something, do something new I've never seen before?
Yeah.
Especially outside the realms of what people have already.
Yeah. Well, I think one of the that's a really deep question, and obviously no one knows the full answer. But I think one thing that has been surprising is how good language is at doing that. So, being able to use arbitrary language and embed that in different ways in order to do the generation process has helped us generate novel things better because language is compositional. So that's helpful. But it's certainly not enough. There's definitely been a lot of work in the community about fine-tuning image generation models, like the various flavors of stable diffusion, like the avatars that I showed of myself. I'm pretty sure that model was a stable diffusion model that had been fine-tuned, in order to produce different kinds of avatars. So fine-tuning is definitely part of that story. What would I like in order to give us even more control over things so that we could build things that had never been seen before? I would love for more embeddings to understand virtual worlds in some way. Maybe that's embedding 3D geometry or embedding information about materials, maybe embedding information about lighting. If we could have an embedding space that had a richer representation of how a scene was constructed, then we could actually compose it. And I think that would give us more control. But I also think that's an interesting research question. I don't think people know exactly how to do that, which is why language is the best thing we have at the moment. But language will never be good enough. We'll never build the game engine of the future where like somebody's prompt engineering, every frame of a video game, right? It's just not possible. So we need better embeddings than text.
I think you probably answered my question, but in a different way. So in the first slide, we talked about the link between graphics and vision. At the end, you spoke about stable diffusion and work like that, where there's vision and language together. So where do you see language in that loop between graphics and vision? I mean, you've answered how much about language.
Right. Yeah, language is a highly compressed representation for, expressing compositionality and more abstract ideas that, humans find convenient. It's maybe one of our superpowers. I love watching birds or like fish. I don't know if you guys have seen swarms of flocks of, schools of fish. The way they turn all on a dime, it's really a superpower. Humans, our superpower, I think, is conversation. The reason that's so amazing is that it allows us to interchange ideas, in a really concise way, at least if we're speaking, if we're not being windy. So how are we going to use that in order to improve the compositionality? I think that's kind of how I see it contributing. I think there's also the other side. We haven't talked as much about how generative models are going to help with discriminative tasks that we often face in computer vision, but I think that's also true as well. Maybe one of the ways that's going to help is that it's a really great regularizer to resynthesize things in lots of different forms. So like maybe we can take language and use it to resynthesize, like, for example, like we can describe like different things we want to do to our data set in language, use a generative model to resynthesize our data set, train a computer vision model on that, get better computer vision primitives. These sorts of things I hope are going to be happening. Yeah.
Okay, so I've got 4 questions on the app. We don't have time for all of them, but I'm going to ask a couple. You can answer one or both. So one question was, can we use Edify to create synthetic data sets to train for different computer vision tasks? How big would the domain gap be compared to real images? And the second question had to do with NERF. Do you think works based on NERF or neural radiance fields can help improve neural rendering or interpolation of frames?
Yes. Okay. So to the first question, yes, I believe that the future is going to include a lot of synthetic data. And I'm really excited about the prospect of using generative models to basically amplify the data that we have. So I do think that's an important area of research. I haven't actually done it with Edify yet. It's on my list of things that I want to do. But I do think that that's an interesting application of generative models is helping expand our data sets for other computer vision tasks. And then the second question was about NERF. I love NERF. I didn't put NERF in the talk because I only had 45 minutes. But of course, NERF is amazing, and there's a bunch of other neural rendering techniques that I didn't have time to talk about that I think are also changing the world. The big problem with NERF, as I see it at the moment, is that it's very static. It's quite difficult to animate things or to build dynamic worlds in NERF, and of course that's what we need. In a fully realized graphics engine, we need the lights to move, we need the objects to move, we need deforming to happen, we need animation, physics, all those things need to be controlled. And so I think NERF is a really promising field, and probably some of you are already working on solving all those things that I just mentioned, and I can't wait to see what you come up with. So yeah, I'm a big fan.
Okay, there's a couple other questions I'm going to ask Brian to address online in the interest of time, but let's please give Brian a thank him for our talk. And if any of you have questions you want to ask Brian directly, he'll be around, so come on up. But thank you. We have about a 15-minute break, and then the final spotlight session for today, followed by dinner in about an hour and 15 minutes.
Thank you. Thanks for inviting me. Had a great time. Yeah. Great. I think I should end meeting for all, right? Okay.